I'm Reva Anmala, and this is my biostatistics project for Math 263. And the question I'm hoping to answer is, does life expectancy decrease in warmer climate countries? Before getting into the data, it's important to understand why warmer climates might affect life expectancy. Warm and hot climates can create several direct and indirect challenges for public health. Directly, high temperatures increase the risk of heat-related illnesses such as heat exhaustion and heat stroke, and this can happen especially in areas that don't have widespread access to cooling systems. Warmer environments also encourage the spread of vector-borne illnesses such as malaria, dengue fever, and Zika virus, because mosquitoes especially thrive in hot and humid environments. These illnesses can significantly impact mortality rates in many countries if they do not have access to vaccines. There are also many indirect issues. Hot climates can place stress on agriculture and water resources, and this can affect food security and nutrition. Warmer temperatures may also worsen air quality, and this can lead to many respiratory problems. In addition to this, energy demands rise in these regions, and not all countries have the infrastructure to support reliable cooling, and this can further increase health risks. To analyze this, I divided the countries into 4 climate groups, and this is based on their average annual temperatures. Group A represents severely warm climates, and this ranges from about 22.5 to 30 degrees Celsius. Group B includes moderately warm climates. Group C includes moderately cold climates, and Group D represents severely cold climates, and this can go as low as -3 degrees Celsius. This study is an observational study, and that means that we are looking at data that already exists rather than experimenting or assigning countries to group. The explanatory variable, which is the factor that we think might influence the results, is the climate category. The response variable is the life expectancy, which is what we're measuring and comparing across the different groups. Overall, the goal of this project is to understand whether climate change relates to the differences in average lifespan across all countries. Before running my tests, I clearly need to define my hypotheses. Because I am comparing the mean life expectancy across 4 different climate categories, my null hypothesis would state that all of the groups have the same true mean life expectancy. And in other words, the average life expectancy for climate A, B, C, and D are equal. Mathematically, this would be written as mu A is equal to mu B, which is equal to mu C, which is equal to mu D. The alternative hypothesis would state that at least one climate category has a different mean life expectancy compared to the others. It doesn't specify which group is different or whether the difference is higher or lower, not that only all that population means are equal. And this is the standard setup for a one-way ANOVA test, which is where I would look for evidence that the climate groups would differ in some meaningful way. Overall, this lays out the framework kind of for the statistical test that I'm going to perform, which I did select to be an ANOVA test. Before running my one-way ANOVA test, I needed to check whether the main conditions for this test were met or not. The first condition is randomization/independence. Because the observational study uses existing country data, I didn't have to randomly assign countries to climate groups, so technically the randomization condition is not met. However, the independence condition is met because each observation represents a different country, and one country's life expectancy would not necessarily affect another's. Next would be the normality and sample size condition, and 3 of the climate groups, which are A, B, and C, they have fairly large sample sizes, which would make the test pretty robust, even if the data isn't perfectly normal. The only exception to this is climate D, which only had 8 countries, so clearly less. And for that group, I relied more on analyzing the visual shape of the distribution of the box plot, and I checked for outliers and any strong skews, and nothing extreme really stood out, so I did consider this condition overall relatively acceptable. And then the last condition is equal variance, which essentially just means that the spread of life expectancy should be similar across all 4 groups. And to check this, you would compare the standard deviations, which I calculated, and a general rule of thumb for this is that the ratio of the largest standard deviation compared to the smallest deviation would be less than 2. And after doing the math, the ratio is about 1.6, which is less than 2, so that does fall in the acceptable range. So the equal variance condition is met. So overall, even though the data isn't randomized, the assumptions needed for ANOVA are reasonably relatively satisfied, so I did move forward with the test. For my methodology, I started by collecting data from both Kaggle and trading economics. And Kaggle provided the life expectancy values per country, and trading economics provided the average temperatures for each country. And after I divided the countries into 4 climate groups, I needed to figure out the best statistical method to compare all 4 groups at once. To do that, I used a one-way ANOVA test. ANOVA stands for Analysis of Variance, and it's designed specifically to check whether the mean of 3 or more groups are significantly different from each other. And instead of doing multiple t-tests, which would increase your chance of error by a lot, ANOVA performs one overall test, and that compares the variation between the groups to the variation within the groups. And if that between group differences are much larger than the within group differences, then the ANOVA will detect that, and it should result in a lower p-value. And in my project, the ANOVA is testing whether climate category has an effect on life expectancy. So the x-axis would represent the climate groups, and then the y-axis would represent life expectancy. And I used Excel's single factor ANOVA tool, and that gave me the F statistic and the p-value that I needed. And I was able to evaluate whether the differences in the group means were statistically significant. And for the visualizations, such as like tables or the bar graphs and box plots that I made in the next slide that you will see, I used Adobe Express, and I was able to create those graphics pretty easily. Here are the results of my analysis. Starting with figure 1, this table shows the descriptive statistics for each climate category. As you can see, climate A has the lowest mean life expectancy, which is about 61.7 years, and that's followed by climate B at 66.3 years. Climate C and D have the highest averages, which are around 71.2 and 72.3 years respectively. And this count also shows that sample sizes are uneven, as I mentioned earlier, because climate A has the largest amount of countries and climate D has the smallest. Figure 2 shows the ANOVA output. The key values to focus on are the F statistic and the p-value. The F statistic is 12.7, and the p-value is 1.39 times 10 to the negative 7. Because this p-value is far lower than the regular significance level, which we are going off of as 0.05, it tells me that essentially the difference in life expectancy across the 4 climates is statistically significant. So in other words, that means that it's pretty unlikely that these differences happen by just chance. And then moving to visualizations, figure 3 shows the box plots for each climate group, and these make the differences in distributions pretty clear. Climate A has not only the lowest median, but also a much wider spread, and climates C and D are a bit much higher clustered on the life expectancy scale. You can also see some outliers in some group, but overall the pattern is pretty consistent. And figure 4 is a bar graph that shows the mean life expectancy for each climate category, and it also includes standard deviation error bars. And that really just shows you that upward trend of life expectancy as it increases from climate A to climate D. And the error bars also show that there is some overlap, but the general differences between the groups are substantial. Now that I've shown the descriptive statistics and visuals, I want to highlight what the patterns in the data actually mean. So if you look at the averages that are listed, there is a very clear upward trend as the climate becomes cooler. Climate category A has the lowest mean life expectancy, around 61.7 years, while climate category D has the highest, which is at 72.3 years. And this is about roughly like a 10-year difference between the warmest and coldest groups, which is a quite substantial gap when you look at national populations. And the standard deviations also are quite interesting because if you look at climate A and B, they show much more variability, which means that the countries within those groups would differ more widely with their life expectancies. But if you look at climate C and D, they are much more consistent. So this could suggest that life expectancy in cooler climates is not only higher but also more stable across countries. And the ANOVA results do indeed reinforce these observations. The F statistic, which is 12.7, does show like a strong separation between group mean compared to the variation within the groups. And the p-value, which is once again 1.39 times 10 to the negative 7, is much below any regular significance level. And that small number that you are looking at does show that the differences that I'm seeing are not random fluctuations, but they are indeed statistically meaningful. So overall, the analysis does show a clear pattern to summarize. As your climate temperature decreases, average life expectancy increases. And the statistical test does strongly support that this relationship is significant. So in conclusion, the results on this slide do show a clear pattern across the 4 climate categories, but what is especially important about these differences is what they suggest beyond just average, like mean numbers. Category A, which is 61.67 years, and category B, which is 66.34 years, reflect lower life expectancies, while category C and D, which are at 71.17 and 72.34 years respectively, represent noticeably higher ones. So by rather than just like showing numerical gaps, these differences do point towards like broader environmental and structural influences that do change with climate. So for example, the higher averages with C and D could reflect like advantages that tend to like more cluster in cooler regions, like stronger infrastructure, more stable public health systems, or reduced exposure to heat-related illnesses. But the lower averages in the warmer categories might reflect the added challenges faced by the countries in the hotter climates, like the prevalence of like mosquito-borne illnesses or resource strains, or like if there are any environmental stressors. But the statistical significance that is indicated by the ANOVA test and its extremely small p-value does indeed confirm that these differences are not random. But the important thing is that the combination of these averages is perhaps probably connected to many conditions that influence the life expectancy of a population. So this data does not provide or prove any sort of causation. They just emphasize that there is a correlation or association between the climate as well as the life expectancy of a country. With that being said, thank you so much. I hope you enjoyed my presentation as much as I did. And lastly, these are my data sets. I derived the temperature one from trading economics and the life expectancy from Kaggle. Thank you so much once again.